So I will just summarize that we had the presentations from Guy Moxey, from Wolfspeed, and the presentation from Ignacio Lizama from Rome. And we are now ready to talk about subjects that the auditorium could address us. The one thing what I would just address from my side is to both of you, that's a question about capacity in volume production. Are we able to serve the demand in the world? And are we able, price-wise, to fit into the application areas who want to use SiC? These are two questions. And the first question I got from a visitor is addressed to Rome. What's the technical innovation to enable E-off reduction? SiC bottom oxide or split gate? That's a question I just got in.
Okay, thank you for the question. I cannot tell you the secret, but what we did also is improve the capacitance inside of our device, the ratios. So that allow us also to reduce the switching losses. So I don't know if that answers your question.
I did not have any feedback from the anonymous visitor. He got the answer. If he wants to have more information, he should address that by email to you.
Yeah, he can contact me directly.
There is a question for Cree. How much of the overall SiC market can you serve with your capacity?
Depends how big we gauge the SiC market to actually be. You know, you look at the market reports for next year, and it's coming up to be anywhere from 600 million to 1 billion, somewhere around that. You look at the market reports for 2025 to 2027, and it's anywhere from 6 billion to 10 billion. So whichever way you look at it, it's a massive demand for silicon carbide. And we are trying to get ahead of the curve at Cree Wolfspeed. It's pretty public knowledge that we're investing $1 billion into a complete state-of-the-art new 6 to 8 inch operable fab up in New York State. We're heavily building that now. I think it's being commissioned towards the end of 21 with going live in 2022, somewhere around that time frame. That's our fab. And obviously as well, of course, being Cree Wolfspeed with our materials supply chain as well, we have to ensure we have enough materials capacity, not only for ourselves, but also for our partners that we sell our materials to. So we are definitely trying to get ahead of the curve on satisfying capacity today and going forward over this next 5 to 10 years. And I'm sure my colleague at Rome will say, you know, the demand for silicon carbide is phenomenal, and we as suppliers have to get in place.
Okay. So the next question which came in is, how does Cree see the advantage and disadvantage of planar versus trench MOSFETs?
Bodo, you and I are old enough to remember silicon when it converted to trench. It must be 20 years ago, 25 years ago, somewhere around there.
About 30 years ago, and I remember that. And you see, I know the historical things. We had, we got smaller devices, the thermals changed. Also, it had some effect into the parasitics.
Correct. And history is repeating itself with silicon carbide. No great surprise. You know, your first question to Ignacio was about thick bottom oxide and split gate. I remember that discussion in silicon. Shielded gate, thick bottom oxide, split gate, all different ways of playing around with capacitance. But back to your question, right now, our generation 3 is still firmly planar. When we look at its figure of merits, it's comparable with everyone's first or second generation of trench. So everyone is in a similar mix right now. And back to the silicon times when it converted to trench, you know, the first 3 or 4 generations of trench from people were the pioneers. They weren't great. It was only when trench got really established and going, you started to see that performance advantage come in. So I think right now, it's right in the mix. You know, you do it, as you said, Bodo, generally you use technology for performance or for cost, obviously. Cost is getting a smaller die size. And obviously the performance is optimizing figure of merit generally. And when you look at the advanced planars versus the newer trench, they're both coming in at the moment to be in similar areas. Our philosophy though is, you know, silicon carbide now is being embraced so much into cars, trains, power supplies, solar today, that manufacturability is a key thing. You know, we've done a lot of trench over many, many years, and we will, you know, develop technologies accordingly. But right now, when people are ramping up in cars and planes and trains, they need something that's consistent and manufacturable today. It ties into your capacity. So it's a balance between advancing technology, but also maintaining capacity and supply and consistency and reliability of proven technologies that people want right now.
Thank you. We have 5 new questions in a row.
Mm-hmm.
The first is, how do you see the competition from GaN in power electronics applied in automotive?
Question to who? Is it Ignacio or myself?
To both of you.
Do you want to go, Ignacio, first?
I can start. It's an interesting question. Actually, we receive this question a lot, how we see the market. And what we see is like, let's say, relatively low voltage is going to be a war between GaN and SiC. I'm talking about 650 volt around. But for higher voltage, we see SiC as the main solution for automotive.
Okay, thank you. The next question is, to Cree, how soon SiC market would switch from 6-inch to 8-inch?
I think we have quite a vested interest in that one, being a lot of it also, of course, stems from the materials. The market is not going to switch until you can get the material at 8-inch to fabricate on. We've publicized many initial documents on our 8-inch material progress. And as I mentioned before, and again, it's in the public domain, our new state-of-the-art fab in New York will be 6 and 8-inch interoperable. But, you know, proving 8-inch as an R&D stage and then taking it into initial volume is very different from worldwide mass production. So I think it's still going to be a couple of years or so until we see true 8-inch entrenched into the market with the reliability that people look towards Wolfspeed to providing.
Thank you. The next question is to ROHM. Increased DVDT helps to reduce the switching losses, but it leads to increased EMI. So ultimately, there will be a trade-off. What's ROHM's recommendation in order to keep the switching loss low and the EMI under control?
That's a good question. Actually, we receive also this question a lot because it's a trade-off. Faster device, you will have problem with the EMI. So we recommend a clean layout, short distance, try to avoid parasitic inductance, but depend on each design. I cannot give you a recipe for all designs regarding that. So we need to investigate case by case.
Okay, thank you. The next question is, what about the voltage stress in the switching? Turn off event, it means that a 1200 volt SiC device can manage peaks higher than 1200 volt. Is 10 times better in terms of life. The plot used by Cree Wolfspeed is for static condition. What about switching transients?
Yeah, you've always got to encounter overshoots, of course. And, you know, when we, and every SiC supplier puts 1200 volts on their data sheet, that is what our rigorous qualification and lifetime studies are taken to. That's continuous, obviously. Most people who use a 1200 volt device will be working from a 800 volt bus or below. So it gives you that extra 400 volts of safety headroom. But I think one important thing to mention for silicon carbide, you know, when we say 1200 volt, it doesn't really start rolling over till a few hundred volts above that. You know, I show that in my presentation that we see first breakdown at 1500 volts typically. Now, we don't guarantee that. Data sheet says 1200 volts, but with a silicon device, it's been optimized so much that a 1200 volt device will start breaking down at 1250. Okay, because it's been around for a very long time and it's optimized for exactly what it is. Silicon carbide generally as a technology does have a higher degree of safety headroom. But of course, if you push it beyond the data sheet value, then that's, you know, buyer beware. And also it will have an impact on long-term reliability. The same as the gate voltage as well.
Thank you. The next question is, where do you see the SiC substrate cost roadmap in 5 and in 10 years? We need a magic ball to look into, but probably you can give some advice.
I mean, I think both of us will say, because ROHM is a vertically integrated company as well, you know, both of us will be quite happy to say that people will still need substrates in 5 to 10 years. You mentioned already migration of geometry sizes from 6 to 8 inch, you know, and beyond 8 inch in the future. If you're looking at a decade time span, you're maybe looking at a 12 inch 300 millimeter substrate. Various ways of thinning them, repurposing them, you know, slicing them in different ways. Utilization of the substrates comes into the mix as well. I think, Bodo, it's back to your initial question about, or the initial question about capacity. People, you know, there needs to be enough substrates to fabricate on to produce the die that goes into the devices that satisfies a $10 billion market.
Okay. Guy, the next question is addressed to you from about ABB is again presenting deposited gate oxides with high K materials, pretending like this is something new. Cree has done research on this and published some results years ago. Why have MOSFETs with deposited high K-gate dielectric not been industrialized? What were the reasons for sticking to SEOI 2? That's very
it's a very
specific.
detailed question. I'm
Yeah.
going to put my hands up here, and I'm just a simple apps engineer by trade. I'm not a device physicist or a material scientist, so I'm not in a position to answer that question with any type of education at all. But if you could forward it to me after this discussion, Bodo, I'll follow up with my brain trust, which we have many of that are into that type of thing, and we can get an answer back to whoever asked the question. Sorry, I can't answer.
That's fine. To state that's not in your sandbox that there are experts is always a good thing, rather to tell the people something that is like a North American actual still remaining president.
No comment.
No comment. And to Rome addressed, how does your Gen 4 transistor position in terms of gate charge in comparison to Gen 3? In other words, are they easier to parallel for high switching frequency operation?
Yeah, we had investigating, and of course, we're also trying to see the parallelism of our devices. And until today, we haven't seen any problem. And if you want to get more details regarding that point, you can contact me directly, and we can discuss it further.
Okay. The next question, do you think the eGaN can actually replace the SiC? From my perspective, will say no.
I mean, you're talking to two silicon carbide people here, so I think we're probably going to agree.
Voltage range that you cover. You cover silicon carbide can cover several kilovolts, while GaN ends somewhere at a kilovolt. So.
I mean, all the technologies have their place, Bodo, I think, don't they? And there's enough silicon market that's not doing a very good job for wide band gap to penetrate in a lot of places. And, Ignacio said earlier on that, GaN, some brilliant GaN at 40 volts, some superb GaN. And I like the approach where they go to get rid of the chip scale, to get rid of the cost of the packaging. And even at 600 volts, 650, where we do cross over in some way, shapes and forms, if I'm looking at designing a 45 watt wall cube to power a tablet with a little flyback, then I think some of the GaN offerings where they integrate the gate drive and the switch together in one package is a pretty good approach. But if you're looking at a drivetrain for an EV car that's switching 400-500 amps, whether it's a 650 volt, 750 volt, or a 1200 volt rated need, then I would naturally be very biased to silicon carbide.
Okay, thank you. The next question is about what percentage of the automotive SiC market will be bare die solutions, and what percent will be silicon vendors providing modules?
And both of us would like to answer that. Ignacio, do you want to go first and I'll follow?
Okay, I can go first. So it's a tricky question, actually, to see how you share the market between the model maker and you providing the silicon carbide bare dies. For high voltage application and SiC-ROHM, we are also providing silicon carbide devices, especially for the 800 voltage volt battery. So, but how we can split the market, this is a question I can answer you now. Maybe you guys can comment on that.
No, I'm with you, because there's no, this is a new market, isn't it? EVs is
Exactly.
relatively new, and there's no great set standards. It's not like an Intel chipset. We are being very open into how we service the market as Wolfspeed. We have our own power modules that obviously we like to promote. Discretes have some place in drivetrains as well, in smaller power drivetrains. But also we realize that tier ones and OEMs have their own customized designs, and they may need some customized modules. So we are very happy, and we are very successful in selling our die to module houses or tier ones that are doing more vertically integrated designs, for them to do their own module approaches. So I think it's very sensible to go to market as die or your own modules, and then you cover as much of the need as we possibly can.
My experience in the past was that an automotive manufacturer probably has not the knowledge to handle bare die the way like a module manufacturer can do. So the risk to fail handling the bare die is too high, that the automotive manufacturers will start really using bare die. It will be probably always an experienced house like Semicon or Danfoss Silicon Power or such people who have experience to do it right, to get the reliability done the way that they have a safe lifetime. So
yeah, I mean, making a module for a powertrain, for example, is no easy thing. 36 die in a module, 48 die in a module, could be sintered. There's lots of complexity in there. So I follow what you say, because there are a lot of expert module packaging companies out there, but also there's some OEMs that want to be very vertically integrated as well. So
yeah, Bosch
yeah,
can do it, but a Bosch is a automotive subcontracting supplier.
yes, yeah.
So
but yeah, we're happy to sell die.
okay, let's get the next question. How do ROHM and Cree address short circuit robustness in current and future MOSFET design? Are further reduction in short circuit withstand time to be expected?
Ignacio, do you want to go first?
I can go first, no problem. So in our latest generation, the one we presented today, we are going to also, we test in short circuit. And for automotive, we're also planning to define the short circuit withstand time. And compared with our third generation, even though we managed to have a lower RTS on, we didn't compromise the short circuit withstand time.
Okay, thank you, Ignacio. Short circuit time, from my historical memory, is something that you stay within the thermal limits, and that has something to do with the die size. The die size and the fast extraction of heat from the die. So
That's exactly what it's all about, Bodo. And we've all said people want to see more economical silicon carbide, which generally means smaller die size, which means more thermal challenge. So
yeah,
the
and
market
thinning
wants,
it,
yeah,
thinning it
thinning,
to a
better,
minimum
yeah, better
will
thermal
get the heat
conductivity.
out.
Yeah. But still, silicon carbide is going to be a smaller die size than IGBT.
Yeah.
So it's going to, whatever we do, it's going to be more short circuit challenged. It's not going to be, you know, I don't think you're going to see 10 microsecond short circuit times in silicon carbide.
We saw it at IGBTs sometimes.
Yeah.
They had up to that, but still.
But there's a lot of gate
We
drive.
have the last 5
go on.
minutes going,
Yeah, sure.
and I have 3 more questions.
Mm-hmm.
Could both of you tell us a bit more about your roadmap of high voltage devices up to 10 kV development?
From our side, yeah, go on, Ignacio.
No, you can go, please.
Yeah, from our side, you know, we've been working on, you know, we class different people different things, but we call it mid voltage. Anything above 1700 volts, we call mid voltage. And you know, we've been very public in our papers and R&D at 3.3, 6.5, 10 kV around the MOSFET. You know, our generation 3 planar, we talked about, you know, our planar versus trench. Our planar is a building block, a solid building block, and our generation 3 is scalable from 650 volts to 10 kV. So we're doing a lot of activity on the 3.3 up to 10 kV. Obviously, it goes hand in hand with the appropriate packaging. But also, I think generally in the silicon carbide market, you know, it's who's going to get the largest die size, because at 3.3 kV, no one wants a 10 amp die. You know, people want hundreds of amps out of a die at that high voltage. So it's perfecting not only the voltage, but also having the right die size to get, you know, 100 amp, a 200 amp, a 300 amp chip as well. But, you know, you're going to see a lot from us in 2021 and 2022 around the 3.3 to 10 kV.
Thank you, Guy. Let's rush. The last 2 questions. Beside automotive, in wind turbine, how is the market for SiC today? The ramp up will come in 3 or 5 years.
Ignacio, do you want to?
Somebody wants to know if the ramp up in wind turbine, how is the market? It's
Well,
I think
generally it's mid voltage. It's higher voltage.
Exactly.
You know, it's above
Higher
1700 volts. So it's going to coincide with how you know, ourselves and our competitors develop the 3.3 and 6.5 kV.
Okay. The last question is on link capacitors. In SiC inverters, do you think there will be a change of technology from film to ceramics due to high frequency switching?
In what application, Bodo? Sorry.
In for DC link in inverter, just general inverter, not specified to an application area. It could be any inverter, if it's wind power or traction.
I mean,
the question is,
if it's turning a motor, if it's turning a motor for an inverter, then it's not going to be switching that fast, really.
Yeah.
If it's a static inverter, you know, doing a DC to a grid tied type application for renewables, you do have opportunity to go to 50, 60, 70 kilohertz hard switched, and then there could be opportunities there.
Gentlemen, our time is nearly at the end. I will thank you for contributing to this successful podium's discussion.
Thank you. Our pleasure.
Thank you, brothers. It's a pleasure.
Good. I think we stopped. Were you still recording?
we are done.
Super.